Okay, continuing on with section 2.6 part 2. This will be the second video for that. So what we're going to start working with now is we're going to start working with what we call a lamina. And a lamina is a sheet that is really, really, really thin, and it's thin enough that it can be treated as if it's a two-dimensional object. Centroid is another word that you will see. Centroid is the geometric center of a lamina. I also threw in this symmetry principle. It is just saying that if we have a region R that is symmetric about a line, I think that's an L, then the centroid of R lies on L. So if you have an object that is symmetric, let's just say we have a quadratic equation. That quadratic equation is symmetric about the y-axis. So that is just saying that the centroid of this object, let's say we cut it off right here. We want to find the centroid of this filled-in area. Well, if it's symmetric about the y-axis, then the centroid will be on the line L if it is symmetric about that line. So that's symmetry principle. Alright, so then going on, a lamina is going to be a shape like this. So what we've looked at just previously in the last video was that we had a rod, and with the rod we said that the mass could be a variable, so an equation. So we could say that rho was some kind of an equation. Well, we can't make rho an equation and also the shape of the object an equation. So that's why when we worked with a rod, we didn't have to worry about the function. We just set it to a unit measure. And then we could play around with what the mass was. The mass was heavier in some places and lighter in others. And so that followed along with an equation. And so we could work with the integral when the mass was variable. But we can't do both the mass being a variable and the shape of the object being variable, because then that would take a double integral. Double integration you will learn about later. We will not learn about it in this class. But there are double and triple integrals. And that's what we would have to do if we had multiple equations to work with, or multiple variables. So this next part we're now going to go into a variable shape. So what we're going to say here when we're working with this lamina is that now rho is a constant. And we're not going to be told what rho is. So a lot of the times we're going to just assume that rho is 1. And really when we are finding what our center of mass is, our rho is even going to cancel out, so it doesn't even matter at that point in time. So we will look into that a little bit later as we go. But let's look at this shape, this region R that we have right here. So this region R is the area underneath the curve of y equals f of x from A to B. And if we want to figure out what the center of mass is of that, then we need to know, first of all, let's just take one little rectangular shape. Okay, and so the first thing that we need to know is we need to know what the total mass is of that. So your total mass of this shape right here, first thing that we're going to have to do is figure out what the mass is. Well, the mass is going to be equal to rho times the area of this shape. So the area of the shape is going to be f of x. I'm going to leave off all the i's and the stars because those are all going to disappear once we take that limit and the sum of all of those anyway. So rho times the height, which is f of x, times the width, which, as you know, what we're going to do here in calculus for integration is we are going to make that d of x. The dx is the difference in our x values, which we take a limit as x, those dx's go to 0, make them very, 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 very small, and that's what gives us the allowance to do the integral. And then the integral is also the sum of all of these values. So we're going to go from the sum from a to b, so the integral from a to b of rho, which is the weight, that times f of x, which is the height, times dx, which is the width. So that gives us the mass of a unit. So before we talked about this, I think I had it written up there last time, but rho is the mass density of a unit area. Right? So we've got rho, and then we need to know what the total area is, which is going to be the height times the width. And that's how we'll find our total mass. Then, to find our moment, so remember our moment is the total mass times the position. So if we want to find the moment of x, m sub x in this case, so this is the moment in terms of the x-axis. Well, what we talked about up here, we talked about what a centroid is. So a centroid is going to be the center of mass for an object or for a shape. So for this, our center of mass, if we make this really, 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 really small, this rectangle as small as possible, well, it is going to be symmetric about the center of this object. So the center of the object is actually the center of mass for each one of these rectangles. So that's what we want to denote here. So we are going to be looking at rho times f of x. I'm going to move my dx out here because we know we usually have that at the end. So far, all we have is the total mass. So we take the total mass, then multiply it by the position. So the position that we are interested in is the centroid of this unit, and so that's going to be at f of x over 2. So halfway up the object. So what that gives us is that m sub x is equal to rho times f of x squared. And then we have this over 2 in here we have to put somewhere. So we can put that as rho over 2. And then we are going to integrate that from a to b. And we still have the dx out here also. And then that is going to be our equation for m sub x. And these will all be written a lot nicer here in just a minute. Then for m sub y, so the moment in terms of the y-axis, so the moment, again for the y-axis, is going to be same thing, so integral from a to b of rho times f of x, and we still have the dx in there. So I'm starting off with the mass unit here, so the mass of the area of each rectangular shape. So that's our mass, and then we need to multiply that position by the position. Well, this position now is in terms of the y-axis. So each one of these rectangles that we look at, the position that they're going to be in is whatever that x value is at that time. So each one of those rectangles is going to be right at x. So we're going to multiply that by x. So m sub y is going to be the integral from a to b of rho times x times f of x dx. And those are our three equations. Okay, so we can look at these three equations a little bit nicer. So the mass of the lamina is m equals rho times the integral from a to b of f of x dx. And so remember, rho is the mass of just a unit measure, so we also have to multiply it by the unit area of the lamina so that we know what the total mass is. So f of x is the height and dx was our width, and so that gives us, well, we know that that's the area under a curve because that's what integration gives us, is the area under the curve. Then the moments, so m sub x is going to be rho times the integral from a to b of f of x squared over 2. So remember again, this is the base. We're using mass unit as our base, and then we have to multiply it by the position. So the position in terms of the x-axis, we want the center, or the centroid of each lamina, so we had to multiply it by f of x, which is the height, divided by 2. We already had an f of x in there, that's why we have f of x squared. Then for this one, we have rho times the integral from a to b of x. Now x is the position away from the y-axis. So every one of these units is going to have a position of x times f of x dx, which we get again back from the mass. So then the centroid, just like we talked about before, x bar is equal to m sub y over m, and y bar is equal to m sub x over m. Alright, so let's look at some examples.